It's a pleasure to welcome Raquel Perales from the National Autonomous University of Mexico, who will speak on upper bound on the revised first Betti number and torus stability for RCD spaces.
Thank you for the invitation. So it's a pleasure to talk here. And let's start. So first, I'm going to give you an overview of the previous and recent results. So in 1997, as you can see here, Colding published a paper in which he actually proved very interesting things. One of the first things that he proved, or the main result of this article, was that the volume function defined on balls of a fixed radius contained in manifolds with a uniform Ricci lower bound is continuous with respect to the Gromov topology. So that means if you have a sequence of manifolds with a uniform Ricci lower bound that also converge to a manifold, and you take balls in each manifold of the same radius, then the volume of these balls is going to converge to the volume of a corresponding ball in the limit space, which is also a manifold. And using the techniques of this paper and actually this result, he was able to prove other results like this second one and this third one. So let me read first the second one. And this second one says that you can choose an epsilon that depends on the dimension of our manifold. The manifold is going to be closed, so compact with no boundary. And the manifold should satisfy this diameter square condition multiplied by the Ricci curvature, and it should be greater or equal than this epsilon n. So we are saying that this quantity is very close to zero. And close to zero, well, it's quantified by this epsilon. Then what we have is that our manifold has to be homeomorphic to a torus if the dimension is different than 3, and homotopically equivalent to a torus if the dimension equals 3. Okay, so this homotopically and homeomorphic condition was later on refined by Cheeger and Colding, and actually they proved that you can change this to bi-Hölder, and we will see it in the next slide. Okay.
Raquel.
Yep.
Hi. Are you assuming some hypothesis on the first Betti number? Because for the second one, I think almost flat manifolds also satisfy that bound, but they can be, for example, new manifolds, right?
Yeah, so actually I'm going to give a bound of the first Betti number in the second slide, and maybe that will answer your question. Yeah. So,
okay.
so wait for the second slide, and maybe that
okay,
answers your question. Okay, and the third thing that I wanted to remark is, well, this third result that actually says that if you have one manifold, so here you have a fixed manifold with no boundary, then there is another epsilon, a small epsilon, such that if your initial manifold is Gromov close to another manifold, which has a uniform lower bound on the Ricci curvature, well, Ricci lower bound on the curvature, then M and N are homotopically equivalent and homeomorphic if N is different than 3. So actually this third result was used to prove this second result, okay? So, but notice that here you have to have M and N should be manifolds. Okay, so now why did Colding wanted to prove the second result or the third result? Okay, so let's see. Actually, the second result, why he wanted to prove that. So Bochner in 1946, as you can see here, proved that any manifold which is closed and orientable with Ricci non-negative then has Betti number, first Betti number, less or equal than n. And the quality holds if M is a flat torus. So how did he prove this? And actually this has to do with with this footnote, so number 3. So this has to do with the first Betti number being equal to the dimension of the one harmonic forms in our manifold. So actually what he proves is that one harmonic one harmonic forms in your manifold, they are parallel. And once that they are parallel, you can get a linear transformation between this space of one harmonic forms and the tangent space of your manifold. And since your manifold has dimension n, then the first Betti number is going to be less or equal than n. And in the equality case, what he does is that, okay, you have your manifold M, then you can pass to the universal cover of your manifold. And if you had these one harmonic forms, or let's say these vector fields, which are dual to your one harmonic forms, then you can also pass these vector fields to your universal cover space. And then these vector fields are actually going to be invariant under the action of the isometry group. And what you have to check is that they are only invariant under translations, which then is going to tell you that your fundamental group can only be a factor of sets. And if that factor, I mean, you have C to some Q, and if that Q is less than the dimension of your manifold, you will end up with M being non-compact, but you assume that your manifold is compact. So that is a contradiction. And so you get that the equality is attained when you have a flat torus. Okay, so Bochner proved that. And actually in the RCD case, there is something very similar that was proven by Digli and Rigoni. And they mimic this proof by Bochner. Well, that's it. And then Gromov and Gallot proved the following thing that was in 1981, so long after Bochner's proof of the first result that is here. And he proved that there is this epsilon that only depends on the dimension, such that if your manifold is closed and satisfies this condition, then the first Betti number has to be less or equal than n. Okay. And another thing that was proven, so because of this result, Gromov actually conjectured what happens. Because of this result, Gromov actually conjectured Colding's result. So actually, Colding is proving a conjecture given by Gromov based on this result that Gromov and Gallot proved. And working towards this conjecture, or very similar to this result, there is this result by Yamaguchi. And Yamaguchi proved that if you have, if you fix a diameter bound in a K, in a dimension, of course, then there exists this epsilon, which is small, such that manifolds that satisfy this diameter bound and this Ricci condition, so very close to being 0, and this sectional bound, and Betti number equals to K, then a finite cover of M fibers over a K torus. And so because of this result, Yamaguchi also conjectured something. He conjectured that this should happen. Very similar to what Colding proved. But later on, Anderson gave some counterexamples showing that this actually cannot happen. And the only remaining case then was what Colding proved. So I guess now I answer what Sergio answered. ask? Sorry.
Like, for example, Gromov and Gallot results tells you that if your Ricci curvature is almost non-negative, then you have a bound on the first Betti number, right? And if we go back to the previous slide, you have the conclusion, like this under the same hypothesis, the conclusion is that M is a torus.
Yes.
But for example, a sphere satisfies the bound, right?
Sorry. Yeah, I forgot one condition. I mean, you have to add that the first Betti number equals 10. I'm sorry. Yes, sorry. Yeah. Good catch. Yeah, I forgot to write that condition. Yes.
Yeah, that the first Betti number is the dimension, right?
Yes, yes. Mm-hmm.
Okay.
Yeah, thank you for. Okay, good. Yeah, so here we have B1M less or equal 1N. Yeah, you're right. Definitely right. Okay. So what are we going to do? So actually we're kind of mimic all the theorem of Colding and the theorem of Gromov and Gallot for RCD spaces. RCD spaces, I'm not going to define them. It takes like a lot of time to define them. What I can say is that they are the synthetic notion of what is a manifold with Ricci bounded below by certain constant. So here we have, so RCD-Kn spaces consist of a metric space such that in a synthetic way, it satisfies Ricci bounded below by K. And here the dimension, so notice the dimension, it's going to be a real number between 1 and infinity. So it doesn't have an integer number. And here it means that we are thinking of this space as having dimension less or equal than this n. So it's not exactly n, it could be lower than that. Okay, so for these spaces, which let me tell you a little bit more. So they satisfy, so here we have a measure. So we can then consider the Sobolev spaces with respect to this measure. And there is a way to define weak upper gradient. So actually the W12 space is a Hilbert space, and there is a Bochner inequality that is satisfied in a weak sense. And also Lipschitz maps approximate Sobolev maps in this space. Okay, so, but let's go back to what are the theorems that I proved together with Ilaria Mondello and Andrea Mondino. Okay, so we have Gromov-Gallot bound on the, here we are going to call revised first Betti number. We also have, I actually have to talk about what is universal cover space for this type of spaces, and what is a fundamental group, which we are actually going to call it revised fundamental group. And then this B1 is going to be called revised first Betti number. Okay, but so what it says is that we also have a small quantity that depends on the dimension, such that when we bound this diameter square of our metric space multiplied by the Ricci lower bound of my space, if it's greater than this small quantity, then its revised first Betti number is going to be less or equal than this n. And this n, I mean, here we are having, I mean, we are writing this L floor and R floor, and it's because this n might not be an integer. So we are taking the integer, the smallest integer closer to n, okay? Smallest, biggest. Sorry, I mean, I guess you know this notation, right?
Yes, biggest.
Okay, biggest, thank you. Yeah, I'm a little bit confused about how to explain this. Anyway, so we have this condition. I mean, we have this bound on the first revised Betti number. And then as Colding did, we also can say that if you fix this dimension, then there exists this delta, and this delta is going to bound again the diameter squared times your lower curvature bound on Ricci, well, the RCD Kn condition. So here's the K. And if you also assume that the first Betti number equals this integer n, well, squares, I mean this integer n, then your space has essential dimension equal to n. So I told you before that these spaces, the dimension can be between, I mean, it's a real number. And actually this essential dimension is telling us that basically your space has a dimension equal to an integer, that there are no pieces of lower dimension. I mean, if I want to be precise, that means that your space has a regular part. This regular part is actually very big in your metric space X. And the tangent spaces or tangent cones at your regular part are equal isometric to Euclidean space of this precise dimension. Okay, so they have a nice behavior. And another thing that happens is that there exists a finite cover X prime, which is also going to be an RCD space of the same with the same curvature bound and with the same dimension, and it's going to be Gromov close to a flat torus of this integer dimension. And if in addition you started with a space with this n, which is a natural number, then actually your measure is going to be C, where C is a positive constant multiplied by the Hausdorff measure of dimension n. And then your space XD is going to be bi-Hölder homeomorphic to an n-dimensional flat torus. Okay, so actually the second statement of this big theorem was also proven by Colding, and I'm going to talk a little bit about it. So that's an intermediate step in order to prove the third part of this big theorem. Okay, so basically I'm going to talk about how to prove this bound on the revised first Betti number and how to prove this stability result. But before doing that, let's start talking about what we do in the smooth setting. Okay, so in the smooth setting, these are like the actors that play in our play. So we have a closed Riemannian manifold M of this dimension equal to n. Then we consider the universal cover space of that manifold. Then we take the abelianized, well, the commutator of our fundamental group, our first fundamental group. Then we pass to the cover. So this is M tilde mod out by our commutator. Okay, and we will, I mean, we can see that this abelianized group of the fundamental group is going to be, so we know that this is isomorphic to this group. And I wanted to write this in red because this, we don't know if it's true when we pass to RCD spaces. So when we try to prove the same thing for RCD spaces, that will cause some troubles. Okay, but anyway, so we know that this group acts in M bar by isometries. And so we can pass to another quotient. So this is going to be M prime. And M prime is actually going to be, so we take M bar and we are going to mod out by a subgroup of this gamma. And this subgroup is going to be isomorphic to this set, to the B1M. Okay, these three, we will later see why we need it. It's just like a technical condition, but actually we have a lot of groups gamma prime. one for each integer. So I'm choosing one for integer equal to 3. Okay, so this is the smooth setting, and these are our participants. So let me start telling you. So first I want to show how to get this bound on the Betti number, first Betti number. Okay, so in order to do so, we are going to use this lemma that was shown by Gromov. And actually, Gromov proves it for k. So here I have a k, which is an integer number. I forgot to write that this is an integer. But anyway, Gromov proved it for k equal to 1, because that's enough to bound the first Betti number. But when we want to prove the stability result, we need k greater than 1. Okay, so we do it in this general way. This general way is written in Colding's paper, and it says the following. Okay, so we pass to this covering, which is just m tilde mod out by h, the commutator of our first fundamental group. We take a point there, and we say that there exists a group, gamma k, actually a subgroup of gamma, which has finite index in gamma, and is isomorphic to set to the P1M. Okay, and it satisfies the following condition. So for all non-trivial elements, this orbit, or let's say when we move the fixed point by an element, by a non-trivial element, it's going to be separately enough. So they are not going to be concentrating around my fixed point, and actually is like a very fixed bound. And the other thing is that I want my generators to move my point, my fixed point, and they will move it, but they won't move it too far away. So it's just less or equal than 2k times this diameter of M. Okay, so now how do we prove this lemma? So in order to prove this lemma, we first want to show it for k equal to 1. So we want this condition to satisfy k equal to 1. So it's just 2 times the diameter of M. Okay, and because of that, then I define these sets. These are just sets. So all the elements in my group that satisfy this bound when I act. This should be my fixed point, sorry. So here I should have a bar. So when I act in my fixed point, it has to move, but it shouldn't move more than 2 times diameter of x plus epsilon. Okay, so then these sets give rise to a group, and then the quotient of m bar by this group, I have to show that its diameter is bounded, and then that because m tilde was proper, then this manifold is going to be compact, and so the index is going to be finite. And also, if I take, I mean, here I'm moving this epsilon, which appears here, okay? And because the action is a nice action, I mean, it's discrete, then actually we have these conditions. I mean, for certain epsilon 0, these spaces are not changing anymore, okay? So then I have some set here. This set, I can think of them as linearly independent. And now I'm going to choose these generators contained in this set. Okay, and actually one does that. Okay, so now here the k appears. So here the k appears. And what we are going to do is we are going to choose these gamma 1 of 2 gamma j, which are linearly independent. and which have maximal J length. Okay, if you have any questions, I know this is a little bit vague. Okay, so then let's pass to another theorem. So we are now going to use this lemma of Gromov to show how to prove this bound. Okay, and this bound is actually just like an application of Bishop-Gromov volume comparison. And for this one, I think I can do a better job. And let me try to explain how to do this. So I'm going to choose in the previous lemma k equal to 1. Okay, so then we will have these generators that move my fixed point at most 2 times the diameter of my manifold. And let me write just T, and such that all the elements in this subgroup that I found are move the fixed point. This is less or equal, move the fixed point by this distance, by this bound on this distance. Okay, so then what I have is that if I take the ball of radius diameter of x, so here I have my fixed point. And because I have this condition, so actually I have these points that are very nicely distributed. They don't accumulate, okay? So they don't accumulate. And actually, if I choose a bigger radius, and let me change color. Okay, so actually we can now define one set that depends on this R. So this R is a positive number. So let me write R greater than 0. And we choose this set. So these are going to be elements of my group, such that, I mean, we have these generators. So then this gamma, I can write it as a linear combination. And I mean, this is an abelian group, and that's why I'm using this notation. So we can write it as this natural number or integer number multiplied by gamma 1 plus L B for our Betti number, gamma B. And the condition that we ask to these LIs is that the sum of their absolute values is less or equal than R. Okay. And LIs, as I told you, they are just integers. Okay. So then I have these elements of the group, so I can act on my fixed point also by these elements of the group. And what is going to happen is that all these elements are going to take this fixed point. If R is big, they are going to just take it to a ball whose radius is 2 times R diameter of X. Okay, so now I have the same picture here when I act on my fixed point using these elements in IR. And actually, I can consider balls whose radius is half of the diameter. So I can consider these balls, and they are not going to intersect because I have this bound, right? So they don't intersect. And to these balls, I apply Bishop-Gromov volume comparison. So what we actually will have is that the number of balls here multiplied by the volume of these balls of radius diameter over 2. So let me just write, I'm very imprecise, is less or equal than volume of this quantity. So it's actually going to be this quantity plus d over 2. Okay. And then, so we use Bishop-Gromov volume comparison theorem. So here we have this ball, which has bigger radius. Let me write it R, and ball, this d over 2. Okay, and so in this part, we can use Bishop-Gromov volume comparison, but also what we know is that this ER, if I choose R greater than 1, or even actually equal to 1, here I'm going to have my set of generators. And I know that the set of generators are actually, I have big one set of generators. So we have here the first Betti number bounded by this, and then we use Bishop-Gromov volume comparison. And we will reach a contradiction if B1 is greater than N. Okay. So that's what I wanted to say about how to prove this Betti bound. And one thing that is used later on to prove the stability theorem is that if we have this fixed diameter of our manifold, then balls with big radius actually contain at least this amount of balls of radius 1/2. And notice that this 1/2 is actually the diameter divided by 2. Okay, so we have this amount of balls, which notice that they grow. Oh, here k should be equal to 1. I'm fixing k equal to 1. So notice that they grow with this exponent, and this exponent is the first Betti number. Okay, good. So now let me okay, let me move on. Maybe I'm going a little bit slow, so I have to hurry up. Okay, and now okay, so that proves the bound on the revised, on the first Betti number, sorry, not revised. And now, how do we prove the stability result? So, so this theorem proven by Colding says the following. It says that, okay, if you have your epsilon, if you have an epsilon that is between 0 and 1, there exists this delta, and this delta, which is very small, is going to bound your Ricci curvature in this way. Okay, and so you have this manifold which is closed, which has this uniform lower bound, whose first Betti number equals n, and let's assume that the diameter equals 1. Okay, so if we have these conditions, then, and this delta is actually smaller than this delta that we found, then we are Gromov-Hausdorff close to a Euclidean ball of dimension n. Okay, so what I'm saying is, okay, and what is close is not your manifold that you started with. We actually had to caution out because maybe we had elements in the group with very short that took our fixed point very close to this fixed point. So what we can say is that this quotient manifold has a ball with very big radius. So this epsilon to the -1 is a very big number because epsilon is between 0 and 1. And this big ball is very close to this big ball in Euclidean space of dimension n. And how does the proof go? Well, the proof goes by induction. So by induction in this dimension n. So we are actually splitting factors of Rn. So the proof that we give for the RCD case, it's a little bit different to this one. We still do it by induction. So let me just quickly read what one should do in Colding case. Okay, and here I'm being a little bit imprecise. So what we have to do is for a center, so for a fixed center, we find points P1 to Pi, and these points are going to help us to split some dimensions. So we are actually splitting up to I dimensions, and we are splitting them because we have nice Hessian estimates and nice, we are close to distance functions, and we also have these estimates. So our harmonic functions are going to be almost orthogonal. Yeah, so here I was very imprecise. I didn't write that these are bounded, but they are sufficiently small, which correspond, I mean, depending on this delta I, which is also very, very small. Okay, so let me move on. Okay, and once that one has this result, which we are very Gromov-Hausdorff close to a ball in Euclidean space, what we can actually show is that these manifolds M bar are going to converge to Euclidean space. Okay, so if you take a sequence of these manifolds bar Mi, then you find that there is a subsequence that converges to Rn. And what you can do after that is pass to the quotient. So let me do that. So you will have that Mi M bar converges to Rn. Here I'm assuming that the bound on the Ricci curvature of this one converges to 0. So it converges to Rn. This is in Gromov-Hausdorff sense. Okay. But now what we have to do is use equivariant Gromov-Hausdorff convergence. So then we will have that this Mi n, and I'm just going to write these are the fundamental groups. So they will converge to some Rn and some group. Okay. So, and this is in equivariant GH sense. Okay, and now to finish the proof, at least if we want to prove that that a space that is covered by this converges to a torus, what we have to show is that this gamma infinity, so, oh, sorry, this is Spanish. So the end play is to show that this gamma infinity equals also Cn, okay? And in order to prove this, we actually have to use the lemma proven by Gromov, in which you find your set of generators who take a fixed point a reasonable amount of time far away from this fixed point. So you don't have things collapsing in the limit, okay? Okay, and basically this is what I already explained to you. Okay, so we take this sequence of manifolds with this curvature condition, and the curvature condition is going to 0. We fix these points, and then we choose this group choosing k equal to 3. So then any Gromov-Hausdorff limit of these new quotients are going to be isometric to an n-dimensional flat torus. And then what Colding does is he does a lot of, well, he uses the result that I told you, the third result. So now we have a manifold. So, okay. So now we are saying that our manifolds are closed. So here n is going to be our torus, okay? So now that our manifolds are close to this torus, then they are going to be homotopically equivalent and homeomorphic to this torus for some epsilon. small enough. Okay. And to prove that the original manifold converges to a torus, well, one only has to show that there is no torsion in our group. So then this mi prime will coincide with our manifolds mi. Okay, so now I have around 15 minutes to explain what do we do in the non-smooth setting. And as I told you, in the non-smooth setting, we need to define what is a universal cover. We need to define what is a fundamental group or some version of fundamental group. And what we actually do is the following. And this was started by Sormani and Wei. So we look at the group of deck transformations between two spaces. So here I have space Y that is covered by X, and the group of deck transformations, well, are the homeomorphisms that satisfy this equality. Okay, and then when Y is path connected and locally path connected, if we fix a point Y0, then we have all these nice properties of the group of deck transformations. So the group of deck transformations is going to be isomorphic as a group to the quotient of our fundamental group divided by the image of the induced map of this fundamental group. We will have a bijection between the fibers and the group of deck transformations. And we will have this homeomorphism between metric spaces. So actually, we are going to say, well, I'm getting ahead of my slides. So first, let us say what is a universal covered space. So what we are going to do is we are going to work only with connected space, and we want a universal covered space to be a space that is also connected. Okay, so it's going to be connected and it's going to satisfy the universal commutative triangle, but I have to remain in the class of connected coverings of my space X. And once that I know what is a universal covered space, which might not be locally simply connected, but still we have a nice group of deck transformations, we say that the revised fundamental group equals the group of deck transformations of this universal covered space of X. I don't know. Is there any question, or maybe let's move on. And what Mondino and Wei were able to prove with this definition of universal covered space and revised fundamental group is that if you start with an RCD space, then it admits a universal covered space, which is itself an RCD space with the same bounds on the curvature and on the dimension. And then in order to prove the stability result, and actually also the bound on the revised first Betti number, with Mondello and Mondino, we have to prove that if X is compact, then the revised fundamental group is finally generated. And actually, this is just a very easy consequence from the work of Sormani and Wei. And another thing that we had to prove is that not only the universal covered spaces are RCD spaces, but also the coverings of our spaces X. Okay, so as it says in this line. So if you have any normal subgroup of the revised fundamental group and you mod out your universal covered space by this group, then you get also an RCD-KN space. And actually, we needed this finitely generated condition in order to prove this. Okay, and okay, so I told you what is a revised fundamental group, And now I should tell you what is a revised first Betti number. Okay, so remember that we are going to have the commutator of our revised fundamental group. And then we have this quotient. So we are quotienting, and this gamma is actually an abelian group. And because of our second result, it's going to be finitely generated. So actually I can define B1 to be the rank of this group gamma. Okay, and it's going to be well defined. So now we know what is a revised first Betti number, a revised fundamental group. Then all the calculations that were done to prove the bound on the first Betti number pass to RCD spaces. So actually there is no difference in these proofs. So any questions up to now? Okay, so if there are no questions, then let me tell you a little bit about how to prove this stability result. So in the smooth case, I told you that what one does is that if we have distance functions, then we use harmonic functions, and we prove that they have nice Hessian bounds and they are sufficiently close to these distant functions, and that these harmonic functions are almost orthogonal. In the case of RCD spaces, there is the notion of harmonic functions, and actually they are used a lot nowadays. But at the time we started this project, what we had is some almost splitting theorem. So what we are going to do is we are going to use this almost splitting theorem to prove that our manifolds that have Ricci lower bound in this synthetic sense, very close to zero, they also are Gromov close to Euclidean space. Okay, so but let me read how this theorem goes. So this is a tool that we use. So this theorem is telling us that if we have a bound which is sufficiently close to zero, so here we have this RCD space, and if we have this condition, so actually this condition is going to look, I mean, it's very similar to the Hessian being super small and the almost orthogonality. So if we have this condition very small, remember that delta is a small number. So actually here we have delta smaller than this, that only depends on epsilon and n. Okay, so if we are able to bound this, then we are able to split our space, so X, that we started, and splitting in which sense? I mean, in the sense that we are measuring Gromov close to a space that has splitted k factors times some y, and this y is also an RCD 0 n minus k space. Okay, so actually, so this is the tool that we use to prove this Gromov approximation. Okay. And okay, so here you see it, and it says if you are able to do that, then you can split. So how do you do this? And in order to split this, we actually have a very similar theorem that was given by Mondino and Neighbor. And this is the almost splitting theorem for RCD spaces. And it's basically telling you that if you choose well enough your radius, then you are able to control what we had before. So this supremum of EPI QI. So here it is. Here it is. No, I am not. Okay, so it's condition number 2. Okay, so you can bound all these 3 things that we have in this theorem. Okay, so we can use this theorem. We just have to be very careful with all the epsilons and deltas that are going on. Okay, and so we are able to do this. And I told you, we just have to be very careful with epsilons and deltas. And we also have to be very careful with this radius that we use. So this radius that we use is actually telling us like how far are our points. Okay, so look at this. How far I can allow my points to go. And for that, so this is actually the last thing that I want to present. So we also proceed as Colding did by induction. And the induction comes from the following. So what we are going to do is, if we have this condition, so our manifold has split Rk times Yk eta. So if our manifold is close to this space, then we are going to split one more Euclidean factor by showing that the diameter of this remaining factor is big enough. Okay, and this diameter bound is actually calculated using that I told you, that using the lemma of this, where we find this group of nice generators, we reach the conclusion that in a ball of radius 1, where 1 is the diameter of my space, that I have R to the Betti number of balls of radius 1/2. Okay, so then I have a big number of balls according with respect to my Betti number in this space. Okay, and if I proceed, so if I prove this lemma by contradiction, then what we can do is take a sequence of this Rk, Yk, eta. This sequence is going to converge in Gromov-Hausdorff sense actually to Rk, because we are arguing by contradiction. So the diameter goes to 0. And then in Rk, I have less balls. Actually, I have something to the k balls in a ball of radius 1. And so we reach a contradiction. So once that we know that this Y factor is big enough, we can split another line using Mondino neighbors results. And this is like the end of the proof. I think there are more technical things that I wanted to skip. So if you have questions about those or about the previous things, please.
Thank you very much for a very nice talk. Are there questions? Yes, Sergio. Oh, you're plotting.
Yeah.
Yeah.
Yeah, actually, this is my first talk of this paper, so I'm not sure it was the best.
That was very nice. Any questions?
Yeah.
Oh, this is something. Go to chat. Okay, well, if there's no questions, let's thank the speaker again. Oh, was there a question?
So in CDKN spaces, you don't have splitting, but you still have like all these like technique of the Bishop-Gromov growth. So you think it would be possible to extend the result in that setting, or that will be like too far?
Like which thing in particular? I mean,
like the torus stability for CDKN spaces. I mean, this is
yeah.
It's
Yeah,
like very
I mean,
strong.
yeah, now I understand what you're saying. Okay, yeah, there is a huge difference between RCD and CD. Yes.
Yeah.
I don't think we could do that. Well, I'm not sure. I mean, I'm not an expert in RCD. I mean, there is a splitting theorem for RCD 0 n spaces, but it's for R's. I mean, you need the R condition.
Yeah. Yeah, losing the splitting condition.
Hmm.
Yeah, but I don't know. It sounds really hard, but I was just curious if like there was something like attempted so far.
Yeah, I don't know. I mean, you know that CD it also includes Finsler manifolds, so I don't know if people like, even if that works for Finsler manifolds, or which other conditions you have to add if you want to split something for these spaces. Yeah.
Yeah. Okay. Thank you.
You're welcome.
Any other questions? Okay, well, thank you again. And our next talk will be in 2 weeks. The speaker is Peter Peterson. And as always, you'll find the time in your local time zone by going to the website for the seminar. So thank you.
Thank you.